Hello and welcome to the final Capstone project presentation for machine learning for data science. This is Team Alpha. I'm Clayton Carpenter. Also on Team Alpha, we have Michael Underwood and Hector Gavilanes. Now, the agenda for today, we're going to be going over the problem definition. We're going to go over the steps that we took for data preparation and feature engineering. We'll also get into some exploratory data analysis and visuals that we made. Then we'll get into the actual model building process, followed by the model performance and selection criteria, and then finally the conclusions that we made about the model and the data set in general. Now, the problem definition. So, what is customer churn? Customer churn is when a customer decides not to renew or purchase again from a company. This can be very costly for companies and cause them to experience a significant loss of revenue. And once these customers are lost, it is generally costly to obtain new ones. So, in this process, we will use the features available to us to predict customer churn. Now, what available features do we have? Two different types. We have customer demographic information in the data set, such as gender, senior citizen status, and dependents. And then we also have the services provided to the customer. And these are things like phone service, whether or not they had multiple phone lines, internet service, and or tech support. So with these features, we're going to try to predict customer churn, which will hopefully lower costs for the company. Now, data preparation. We took 3 steps in our data preparation. We converted some data types. There were some that were loaded in as categorical when they should have been numerical. We also created dummy variables for the remaining categorical variables. And then we did a test train split in order to train and test the model on the data. Now, for the data types that were converted, as you'll see in our code here, monthly charges was generally pretty straightforward to convert to an integer. However, total charges had some null values which did not allow for the as type int conversion steps that we did for monthly charges. So for those instances, we had to use a label encoder. After the data was transformed with the label encoder, you'll see the screenshot on the left that all of the data types that should be integers show up as int64. The next step in the process was to convert the remaining categorical variables into numerical, and we did this with the pandas get dummies method. As you'll see over to the left, this is what we want the data to look like, where a single column such as internet service will now be broken up into separate binary columns that would be a 0 or 1, for example, if they had DSL, or a 0 or 1 if they had fiber optic, or no internet service, and so on. In this next set of code that we see here, this is us actually calling that getDummies method and specifying what dummy columns we want to be the target. And then finally, we are separating the X from the Y, which is the target variable, data sets. And then finally here on this next slide, we are actually splitting the data into a train test split with 25% for the test data set and 75% of the data left to train on. And here I'll pass the presentation over to my teammate to go over the feature engineering process.
Hi, my name is Hector Gavilanes. In this section, we will prepare and select the best features. During the encoding process, we attempted to convert total charges column to integer. It is because this feature contains empty character that produces an error. The way that we handle the error, we fill them out those empty characters with a median. The median is less affected by outliers. That's the main reason that we chose it. Some features were not balanced. Therefore, we used normalization. Normalization is useful to scale the data to a specific range between 0 and 1. Feature scaling is used to prevent bias toward a specific range of values. Exploratory data analysis, or EDA. In this section, we will use some graphics to recognize patterns. First, we go over some basic statistics. The dataset contains three numeric features: tenure, monthly charges, and total charges, which was already encoded in the previous section. There are 15 categorical features, and there are no missing nor duplicate records. Now it's time to go over correlation analysis. The data frame has multicollinearity, which are represented with the darker blue. Monthly charges is highly correlated with multiple services. The fiber optic internet service is the most expensive one. Moreover, all the services are correlated among each other. For instance, we have streaming TV and streaming movie. In this table, we can identify the high correlation values starting from internet service all the way down to streaming movies. We will not consider features with correlation values higher than 0.7. In this summary report, we can spot very quickly some problems. Tenure and contract are correlated. In addition, monthly charges is highly correlated with 8 different features. And phone service is not balanced. Normalization addresses this problem, or we have the option to drop this feature as well. Inference. We will concentrate on the 26.5% from the pie chart. This represents the customer churn rate. The evidence suggests that the following characteristics increase the probability of churn: young generation, low tenure, month-to-month plan, fiber optic internet service, high monthly charges, no dependents, no partners, and the phone service. Now that we have a better understanding, it is time to go over some feature selection. In this section, we will choose the optimal features for the classification model. Information gain. This is a quick filtering technique that goes over all the features. However, it includes highly correlated features. Contract, in this case, is the most important feature. Moreover, we have total and monthly charges that are not correlated. They have about the same importance, therefore, they can be included in the model. Recursive feature elimination, or RFE. This indicates the optimal features that the model should contain. In this case, 15 features are enough to predict customer churn. Selected features. The following services or products, highlighted in red, were not included due to high correlations. We believe that gender does not provide valuable information. It is important to understand the data frame and not to rely on automated feature selection algorithms. Very often, these techniques include highly correlated features or features that do not explain well the problem at hand.
Hello, my name is Michael Underwood, and today I will be going over model building, model selection, and parameter fine-tuning for our presentation. After we explored and prepared our data, selected the best features, and engineered those features, it was time to test models. We have chosen 6 models to explore, and they are logistic regression, decision tree, random forest, gradient boosting, support vector machine, and XGB classifier. Now, in order to train all of these models, they had to be imported into our Python, which you can see on the right-hand side. We used a training and a testing set composed of all of our selected features and post pre-processing. All of these models were ran without parameter fine-tuning, which would be done later, and we are expecting them to give us an accuracy score as well as an AUC score, which we will be using to compare. After all the models were run, we have our list of accuracy scores and AUC scores. As you can see, logistic regression outperforms all of the other models. Gradient boosting and SVM are close behind, but still logistic regression outperforms both of them and will ultimately be our chosen model after we go through all the parameter fine-tuning steps. Here we will look at our model performance and the selection process in which we end up with our logistic regression model. In order to fine-tune our logistic regression model, we will take a look at the parameters. Our first code block on the right-hand side will list a hyperparameter search space. We look at the regularization parameter, the solver, and the max iterations. The second coding block, after we set up a LR classifier object and a random search object, will be used to go through all of our X and Y training data to find all the parameters. And then we use a random search on the best parameters to give us the best hyperparameters that they found. We then train the classifier with the best hyperparameters on the full training set. And as you can see in the third block, we are expecting to get out a new accuracy score and a new AUC score and compare it with our non-fine-tuned model. So after we have fine-tuned our model and selected the best hyperparameters, we are given a new accuracy score and a new AUC score. As you can see, when compared, the accuracy score drops just a little bit, but our AUC score increases significantly. Here we found out that our best hyperparameters are a C score of 0.664, max iterations of 400, and our solver is LBFGS. We also did some other fine-tuning on some other different models to see if any of them could outperform our logistic regression model, which ultimately they did not. But we did pipeline tuning on k-nearest neighbors, decision tree, and our logistic regression model, in which case the logistic regression model stayed relatively the same. The other two went up, increased in AUC score, but ultimately did not surpass the logistic regression model. We did chosen parameters for the XG boost, which also increased its accuracy, but its testing accuracy did not increase higher than the logistic regression model. And we also tested out class imbalance, in which the test accuracy of our logistic regression model dropped severely. The AUC score went up, and ultimately we did not decide to use.
Final model and conclusion. We prepare an ensemble model with logistic regression and gradient boosting. It scores 75% for accuracy and a ROC area under the curve of 84%. We incorporated a threshold of 0.3 to create a balance between recall and precision. To conclude, our data-driven analysis has provided valuable insights into customer churn patterns. which is an important indicator for subscription-based companies. We have identified a distinct group with a higher probability of churn, characterized by their single status, lack of dependence, lower income levels, preferences for shorter contracts, and tendency to avoid higher monthly fees. For instance, the fiber optic internet service. Understanding these factors can help managers identifying products or pricing plan weak points, operation issues, as well as customer preferences and expectations. This concludes our presentation. Thank you for watching.